All right, we are back. Let's come back to this. Any questions otherwise? So what we're going to do now is we're going to formally define what it means for a Turing machine to actually accept or reject this input. And I mentioned when we did this computation earlier, those things are called configurations. So the idea behind configurations is it's just a string based off what's on the tape, and then it's just a computation really is just a sequence of those configurations. So that, yeah.
Quick question as you change it to accept. Do you have to specify that it's final, or is it just implied as final?
Yeah, it's just implied.
Okay.
Yeah, so you don't need a double circle. Yeah, single circle's fine. As long as you say that it's called QAccept, yeah.
So does this strict work for all numbers? Like if we skip 3 times, you get 1,003?
Yes. Yeah, so if you had an extra transition to like Q3, Q5, and then back, that'd be powers of 3. Mm-hmm. So you can get any fixed power like that, yeah. Other questions? Okay, so in order for a Turing machine to accept, what we wanted to see is that if we actually did go through the rest of this computation, we should see at the very end the state that's written under the tape contents. That is QAccept in order to accept the input. And it would be QReject if we wanted the computation to be rejecting. So we're going to define a configuration. So it's not really a formal definition, but it contains the tape contents, tape head location, and current cell. More formally, it's a string in gamma star, Q gamma star. So what in the world does that mean? It just says a bunch of tape characters followed by a single state, which represents the state that we're currently in, and tape characters afterward. So as an example, if we look at the starting configuration over here, this one, that corresponds to Q0, so a starting configuration for the Turing machine above would be Q0, 0, 0, 0, 0. So all it just means is that we are in Q0 right now, and we're looking at the cell directly to the right of the name of the state. So in this case, I'm looking at that first 0 in state Q0. And the rest of the non-blank portion of the tape is 0, 0, 0, 0 currently. But the next configuration said that once we saw that 0, we're going to move right, and then we're going to first change that 0 to a blank. So the next configuration will be blank Q1, 0, 0, 0. So remember, we're always looking at the cell directly to the right of the state name. So does that tell me the tape contents, the location of the tape head, as well as what state we're in? Well, it clearly tells me what state I'm in. That's good. Does it tell me the tape contents? Yeah, but what about that infinite sequence of blanks after? Do I need to include an infinite sequence of blanks?
So writing the Q0 and Q1, that's not actually like you're modifying the input state Q0 and Q1,
No.
you're just saying it's like
A configuration is
status.
a configuration is literally just a string of characters that happens to have a single state name in it. Okay?
So if the input, if there's nothing after the 0, then it's the end.
There's no end because it's an infinite one-way tape, but there's an infinite sequence of blanks of which I don't need to include them.
You don't need it because you just need the actual.
Yeah, but if I go over into the blanks, then I'm going to include it in the configuration.
But you would only include it in the configuration.
If I see it, yeah. Yeah. So for example, when we did this transition from that guy right there to the next one, we had the configuration blank x00 q30, and then after one transition, that gives us blank x00, and then we changed it to a blank q4 blank, I think. Oh no, q2. So because if I try to move right, there's nothing currently in the configuration to the right of where the state name would be. So that's why we put a blank after it. Just like when we're doing the actual computation, we look at the blank right after where the input originally was. So if I ever need more blank characters, I can just include them in the configuration. Okay? So this process right there is called yields. So we say that config C1 yields C2 if after one transition from C1, the resulting config is C2. So all it really means is that if we are in the first configuration and we apply the only transition we can do because the machine's deterministic, we end up with the second one. So all it really means in terms of like say a DFA is we apply a transition, a valid transition. Okay. Cool. Is the starting configuration unique for all inputs? So, sorry, if I fix an input in a machine, is the starting configuration unique? Yes, because the input, if I fix it, is the same. The starting state is always the same. Is the location of where the tape head starts always the same? Yeah, it's always at the beginning of the tape. Well, what is the starting configuration if the input is W and the starting state is Q0? Q0W. Always. So that's always the starting config if the start state is Q0 and the input string is W. Okay? Say that a config C is accepting if the single state in it is Q accept. And we say that a config is rejecting if it is Q reject. So we have exactly one starting configuration, but we may have many accepting configurations because the state Q accept can be anywhere in the configuration, as well as the other tape contents, they could be anything. But the starting configuration is unique for a given input and machine. Okay? Cool, so let's define a computation. Is a sequence, well, I don't know how long it is because I overwrite the input, So it's a sequence of configs, C0 up to CM, let's say, where C0 is the start config and CI yields CI plus 1 for all I. So it's almost exactly the same as when we defined it for DFAs. You start in a start state, and the sequence of states is just that you applied the valid transition in between every pair of states along the way. So C0 is the start config, you apply a transition, you get some config to get C1, C2 is another transition, and then all the way through. Any questions about that? Yeah.
So can we say for any kind of input state that the configurations would be consistent?
What do you mean consistent?
Meaning, like, they would all be the same for any, for that function?
For the, if you fix a machine and string, so
Because we're doing the same function.
yeah, we have to be careful because since the machine could run forever, it may not have a computation. But let's assume it does. Then the computation is unique, yes. And whether it is an accepting computation or rejecting computation is always the same. It's always preset if you have the machine and the string fixed. Okay? So we say computation is accepting if CM is accepting, and we say it's rejecting computation if CM is rejecting. In other words, if you went through the entire machine and you ended up at QAccept, we say that we accept that input. And if you ended up at QReject, we reject that input. So here, it'll come up a few more times that it's important to distinguish between accept and reject here instead of accept and did not accept. Those did not accept versus reject, those are different things. Because we're defining another type of computation called a halting computation if CM is accepting or rejecting. So it just means, did the machine stop on this input? That's all it means. And one more definition, I'm sorry, I think. So, actually two more, sorry. L of M, where M is a TM, is the set of all strings such that M has an accepting computation on W. So this is almost exactly the same thing as for DFAs or even PDAs or NFAs. As long as it has some accepting computation, we put it in the language of the machine. Okay? So we say a language, L, is recognizable if it is the language of some Turing machine. So for example, the 0 to the 2 to the n example that we did before, that language is recognizable because we just made a Turing machine that has that exact language. Okay? But there's something that we need to note here. For the definition of the language of the Turing machine, could it possibly run forever on the inputs that is not in it, that doesn't end in QAccept? Could it run on other forever on other inputs? It is possible, yeah. So we may need to, and we will, make a distinction between machines that will halt on the strings that it does accept in the case of recognizing, or it halts on every input, which is something that we may want to think about when we're designing programs, because we want every input to halt. And it'll turn out that these two things are different. But if a TM halts on all inputs, then its language is decidable. So if you make a Turing machine, that language is already recognizable, but it may or may not be decidable, depending on whether there's some string that runs forever or not. So examples of decidable languages, 0 to the n, 1 to the n, 2 to the n, because we could have a machine using our idea from before where you cross off 1, 0, cross off 1, 1, cross off a 2, then scan back. Would that strategy run forever on any, is there some input that will run forever? No, because every single time I'm taking 3 characters, I'm crossing them out, and the input is finite. So therefore, when I make the final check, I have a finite amount of time to actually go through the entire computation. So that machine will halt on all inputs. And so the language, this guy, is therefore decidable. So we actually just showed that there's a decidable but not context-free language. And we'll actually see that all context-free languages are decidable, but we'll get there eventually. And the other example was 0 to the 2 to the n, and it leaves 0. That's another decidable language because every single time we're taking out half of the zeros that are still left, and then when we come back, I have fewer zeros to work with, and the input was finite at the start. So therefore, it doesn't run forever.
Can you know?
Yes, every decidable language by definition is recognizable. It's just an extra qualification. We will see languages that are recognizable but not decidable, but we'll get there eventually. Yeah.
And these work backwards too, so like regular languages are also decidable.
Yes.
Okay.
Yeah.
Figures, but
So,
you're drawing-
yeah. If, here's a great exam question, I won't include it though. If we have a Turing machine that only scans right and never changes anything on its tape, what is the language of that Turing machine? Well, it may or may not be finite because it may have an infinite possible set of inputs that it may recognize. Is it regular? Yeah, because that's just what a DFA did. Right? It's just what a DFA did. It just scanned only right across its input and never changed anything on its tape. So the notion of being able to come back and change the contents of the tape, that changes the whole game here. Okay, yeah.
So just to summarize, so recognizable language would be something that is accepted, right? Or does it have to be
It's,
simple reject?
if you make a Turing machine for a language, it already is recognizable. Yeah. For a recognizable language, I require that all the strings in the language halt and accept. Yeah, I don't make any qualification as to what the other strings are going to do. They actually, in one of the theorems we'll prove, will require that they all run forever, all the other strings. So, but the ones that are in the language have to halt and accept. Yes.
Decidable, it's just the string.
Everything halts. Yeah, and correctly says the right answer, but yeah. As long as everything halts and says the correct answer, it's decidable. Other questions?
You said all recognizable is decidable?
No.
No. Okay, right.
Decidable is an extra qualification on the language. So every decidable language by definition is recognizable, but not necessarily the other way. And it actually is not true the other way. Other questions?
I have a question.
Yeah.
So from the picture that we drew before the break,
Mm-hmm.
every transition, if you have a transition from the queue accept, it should go to queue reject.
No. What I said here is that all the unwritten transitions go to queue reject. Or were you referring to something else?
Right, so for queue accept does not have any queue
Yes.
after, it
Mhm.
should go to queue reject.
Well, we say that the computation stops if you hit queue accept or queue reject. So once you enter those states, the computation's done.
So it's wrong to have something leaving queue accept.
According to the definition in the book, it's okay, but it's never going to be used anyway. Yeah, that's why I mentioned up here. Technically, the definition should say that the state that you're in is any state that's not the accept or reject state, but the book allows those states in, but it's not going to matter because the machine stops at that point anyway if you enter those states. Okay? Cool. So let's keep going unless there are other questions. Okay, well, I'm going to suggest another idea for trying to decide 0 to the n, 1 to the n, 2 to the n. So the idea that we had was cross, 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 go back, cross, cross, cross. And you may be wondering, that's horribly slow, right? That runs in n squared time, and I can do it in linear time, right? Wouldn't you want it to do it in linear time? So I'm going to suggest an idea. So, but do we care about efficiency in this class? No. But you may want to care about efficiency wherever, if you're working on Turing machines. But let's suggest an idea like this. Let's suppose instead of 1 tape, I have 3 tapes. And so the input is provided on the first one, let's say, with blanks after, and the other tapes start out blank. Well, what could I do to make my life a lot easier here if I want to use those other 2 tapes? I could ignore them and use the same thing we did before, but could I make the other tapes useful?
Split up the zeros, ones, and twos.
Oh, sorry?
Like, split up the
Mhm.
ones and twos on the other tapes.
Yes. Yeah, exactly. So what I could do is I just scan right on the first tape until I get to the 2s, and then put them on the, let's say, 3rd tape. So, and then blank them out. So I'm going to blank these out and put them on the 3rd tape. And then, similar idea, let's blank out the 1s on the first tape and put them on the 2nd tape. Now what do I need to do? Well, how would I check if the input really was 0 to the n, 1 to the n, 2 to the n? I just scan right across all 3 tapes simultaneously until I see what on all 3 tapes? Blank on all 3 tapes. Did that just take linear time? Yeah, it took linear time to scan all the way to the end, linear time to scan all the way back, and then linear time to scan once last time. So that is actually more efficient. And you may be concerned, well, could a multi-tape, it's called a multi-tape Turing machine, could multi-tape Turing machines recognize or decide more languages than single-tape Turing machines? So these are called multi-tape TMs. What's that? We'll show their equivalent. But it seems like certainly they can do things faster. That's no issue there. But it's just can they recognize or decide more? Well, could a single tape Turing machine accept more than a multi-tape Turing machine can? Well, we'll see how that works, but could a multi-tape Turing machine accept more than a single tape machine can? Well, it certainly accepts at least as much, but could we convert a multi-tape machine into a single tape machine that accepts the same language? Well, if I wanted to, so in this case there are 3 tapes, but in general I may have many more. How could I employ what we just did on all 3 of those tapes onto a single tape? So there are things that we need to worry about here. Like on this first tape, I may have a different tape head location than the other tapes. And I may be looking at different symbols on all 3 tapes, or all K tapes in general.
Make them all start from the same.
Yeah, they initially start at the beginning, but the first one, I'm going to keep the last 2 the same, at the same place, and the first one's going to go all the way across. So I may not do the exact same forward-backward motion on all of the tapes. It may be completely different. Yeah.
Would you want, if you're converting from 3 tapes to 1 tape, would you want to end that special symbol between each tapes?
Yeah, so that might be a good idea. Maybe what we can do is let's keep track of the computation we're doing with these 3 tapes on a single tape, and then somehow mark in each of where those 3 tapes was, where the tape head originally would have been. So here's an idea. So we're going to make a long tape, and then put a special delimiter in between each. So that gets us part of the way there. It tells us what was on each of the tapes previously. But in this single tape machine, I only have exactly 1 tape head. But in the original, I had 3 tape heads. So what could I do? Any suggestion? Yeah.
Could you start reading and cross off the first one and then say just keep going until you get to the pound symbol and cross that next one off?
I could do this sort of crossing behavior, but then I won't necessarily remember what the symbol was at the beginning, which could cause problems.
We can only convert to 1 space at a time.
Yeah, you can. Well, that's not necessarily a problem. I can just go across and then see if I have some special delimiter on the symbol that had the tape head. Then I can figure out what to do in that case. So we're going to use a strategy which is called dotting. Okay. So the idea here is we're going to increase the tape alphabet size by 2. So for every symbol, A in the tape alphabet, add a new symbol, A with a little dot on the top. And don't think that this dot is a special behavior of the Turing machine. All it is just another symbol name. But to us, it represents, if the tape head was looking at this cell and it had the value A. Okay?
As in, the tape had at that point in time, it was looking at it.
Yeah,
Previous time.
yeah. If we were simulating it with the multi-tape, that's where the tape head would have been. Okay? Other questions? All right, so if we happen to have, maybe not this tape head, but let's say right here for the second one, then the tape contents would look like this. Okay? And so now, remember, the single tape machine will only have exactly one tape head to work with. So how do I carry out a transition? Well, here's what I do. And here's something that's really important. Is the number of tapes from the original multi-tape machine, was that number K fixed? Or could I add tapes along the way? Sure. So the rule of the game is, once you make a multi-tape machine, the number of tapes it has is fixed. Okay? So, if the number of tapes is fixed, do I know exactly how many of these sections there are? Yes. So, to carry out a transition, So I'm going to say the idea and then we'll think, is that a good idea? So what I'm going to do is I'm going to zoom all the way to the left-hand end of the tape. Then I'm going to start scanning right. And now I'm going to remember all K symbols on each of the tapes. So for example, if I'm starting here and I'm starting to scan right, I'm going to remember tape 1, or whatever its name is, had a 0 on its what it was reading as the character it was reading, if it was in the original machine. So I'm remembering tape 1 was reading a 0. Then I'm going to keep going, and I'm going to remember tape 2 was reading a 1. And then I'm going to keep going until I see tape 3 was reading a 2. But how is this machine, this single tape machine, going to remember all K symbols? Because if there are, say, V symbols, then the number of possibilities is V to the K. How am I going to remember all that? It's fixed, isn't it? The number of symbols is fixed, and the number of tapes is fixed. So I remember it in states. So I'm going to have V to the K different states. And then at that point, I know exactly what transition to do because I know exactly what cells I remembered along the way. So start at left-hand side and start scanning right. Remembering, I can't remember how to spell remember. Remembering which K symbols were dotted. And I'll put in parentheses in states. So I'm going to have a ginormous number of states to remember, but it's finite. That's the important thing. And it's fixed, which is even more important. Okay? So once I remember in states what transition to do, and I'm all the way at the right-hand end of the tape, what should I do? Start scanning left. Until what happens? I find a dotted symbol, and then what do I do with it? I don't need to remember because I already remembered it. I carry out a transition of the original machine. Okay? So then start scanning left, carrying out the appropriate transition and dotting symbols as necessary. Yeah, so I'll never ever ask for you to produce a multi-tape machine and then convert it to a single tape machine, because that'd be absolutely ridiculous. But the point here is to see, can you actually carry through this out in principle? And it seems like it can. But I think there's still one more problem that we need to figure out. What if, for example, I'm right here reading that 0, and in the original machine, I said move right. What would I be pointing at now in the single tape machine? The pound symbol, right? Is that a symbol on the original tape? No. So what do I need to do? I need to put a blank symbol right there. What do I need to do to the rest of the tape? Push it out one position. So if any transition moves right into a pound symbol, push rest of tape contents right one position, and then mark original cell as blank, because that's what the original machine would have done. Okay. So even giving you multiple tapes may make your Turing machine a lot faster, but it can't recognize anymore because I can convert from a multi-tape machine into a single tape one. And so this process is called simulation. So the idea here is that whenever we're trying to say, okay, here's a new Turing machine model, I want to be able to, with a single tape deterministic machine, simulate the potential other model. So here, I'm having a single tape machine simulate a multiple tape machine. And then as we're going to talk about a few different what are called variants of Turing machines, and then we'll try to see how to use that single tape machine to simulate this other machine. Okay? In other words, can I convert from this new model back into the single tape deterministic model? Okay? Any questions? Yeah.
So the trade-off between the two is tape space and time?
Yeah, tape space and time. So here we're, until we get to the P versus NP stuff, which I hope we do, we're not worried about like how much time or space is taken up here. But it certainly takes less. It can't take more time with the multiple tape one. Yeah. But we will worry about that. Here's a good theorem. I've proven it, and it's exercise 7.49 in the book. I won't prove it here, but it's probably the hardest problem in the book. So I'm not requiring you to solve it. If a TM runs in little o and log n time for all inputs of size n, its language is regular. Okay? So it's just, if you can bound the amount of time it takes, you can actually say stuff about the actual language that it recognizes. And so this if a single tape deterministic machine? Well, the language 0 to the n, 1 to the n is not regular, but with a 2-tape machine, I can do it in linear time. But what this claims is that you can't do it in less than n log n time for any Turing machine that exists. So it's a pretty cool problem. But any other questions? Anyone's brains fried yet? Okay. Example of example of everything.
Well, I mean, just like that thing, this dotting.
It'd be really, really long and difficult.
Okay.
Yeah, it's not really important in terms of actually doing the conversion. What's important is that we can design a multiple tape machine, and that is equivalent to single tape.
Oh. Okay.
Yeah, I'd never ask for you guys to convert from multiple tape to single tape. That's ridiculous.
Okay.
But the process certainly can be done by a computer, and is somewhat straightforward. And it actually does give a Turing machine with the same language. That's the important part. So, like, if on a homework I say, make a 4-tape machine for whatever, or a multiple tape machine for whatever, then you know that it's equivalent to some single tape machine. That's the important thing. Yeah.
So as per the third kind of rule that we made, where shifting the tape right and putting a blank symbol in there.
Yeah.
So essentially, there's not like a hard and fast rule that when you see, although our first examples, when we saw the empty space, we changed characters or changed character. That doesn't necessarily have to be. It would be
No, yeah, it doesn't
the machine
have to.
itself, how you set it up.
Yeah, yeah. Yeah, so we could have a machine that always moves right on any input character. And so therefore it would never accept anything. But yeah, so usually when we hit the infinite sequence of blanks, we move left, because if we move right, then it's game over from that point. But it's almost always move left. Yeah. Other questions? So let's do one more, and I'll do an easier one because I know you guys want easier things after that. So no, after today, I understand. So I mentioned that for Turing machines, you can only move left or only move right. What if I was an entrepreneur and I said, I'm going to allow you not only to move left or right, but you can also stay exactly where you are and not move. So what is called a stay put instruction. So a stay put Turing machine. So in addition to left and right, can also do an S instruction where the tape head does not move. So it can do exactly what it could do before, but it could also stay exactly where you are and change the symbol on the tape if you want. So clearly, any stay put Turing machine can do what a normal Turing machine can. But could a normal Turing machine simulate a stay put machine? Yeah, how? Yeah, well, what I could do is, well, if it was a left or right transition before, well, it's still a left or right transition now, so that's no problem. What if it was a stay put instruction? Well, should I move left then right? No, what can cause a problem? I could hit the left-hand end of the tape. Am I safe moving right then left?
Yeah.
Yes. And what do I do with the tape? Do I change the tape contents? No. So if a S instruction is found, simulate it with a right, then left transition without changing the tape. Okay, so all we're doing here again is simulation. We're simulating the stay put machine with a normal machine that doesn't have stay put. So if it was a left or right transition before, I'm still going to do exactly what it did before. I'm going to do exactly what the machine would have normally done. But if it was a stay put instruction, I'm going to simulate it with a right then left transition. Okay? Yeah. Yeah. So I'm just going to be simulating it. Any questions about that? I can do one more or let you guys go early. You want one more? Okay. So let's do one more quickly. So I'm going to call a left reset TM to be can do left-right transitions as normal, but also, oops, not D, also do a reset transition where the tape head instantly moves to the leftmost tape cell. So it can do at least what the normal model would have done, but it also has this special instruction where it instantaneously jumps to the leftmost cell in one transition. Okay? Well, clearly it can simulate a normal Turing machine, but could a normal Turing machine simulate this guy?
Yeah.
Yeah, how? Yeah, a self-loop that moves left, but the problem is I might hit the left-hand end of the tape, and I don't know where it is.
So you'd have to have a special symbol.
I have to add a special symbol and do what with the input?
Move it down.
Push it right one position. So to simulate I'll abbreviate it as LRTM, push input right one position, and before that I meant mark the first cell with special character. To execute a reset transition, scan left until special symbol is found, then move right. I know it's a bit of a pain to write these out in English, but the idea is pretty clear. In order to simulate the reset transition, I have to have some character there to tell me where the left-hand end of the tape is, and I just scan left until I see that special symbol, then I move right one position. Yeah.
So we could make a lot of these definitions simpler. We could just define an insert, right, function that would
Mhm.
actually do that, right?
Yep. So yeah, you could have a insert Turing machine where directly to the cell to the right of you, you insert as a blank character right there, possibly. Another one you might want to say is each of the cells has a stack that you can push or pop on. And then what you do is, in order to simulate that, is you have the cell followed by whatever is on a stack with delimiters in between. So it's like the multi-tape simulation.
So the
Yeah.
more Turing machines that we define, the more power in our toolbox that we can.
Well, since we can simulate it, we don't get any more languages, but in terms of being able to make simpler Turing machines. Yeah. But the base model is the one we're still going to always work from. Other questions? So I'll let you guys go 4 minutes early, and I'll see you on Friday.